Alright, so in the last class I defined what is cos theta. So assume that I have a V which is an inner product space, V and inner product space. So we had, if theta is the angle between two vectors, then we defined cos theta is equal to uv divided by length of u into length of v. This is what we had done. Alright. So there, from giving this definition, I just went directly to the perpendicularity or orthogonality, fine, to get you some ideas about parallelogram law, Pythagoras theorem and so on. Now I would like you to compute this and then proceed further in those directions. So just some examples here. Examples. First example, so we showed that there are certain vectors in R2 which are 0 under the standard inner product. So let me again look at R2 itself with a standard inner product. Fine. So under standard inner product, if I look at the vector, say, or in R3, let me put it R3, then I want to find the vector this and 1, 2, 1. Inner product of this is nothing but, just compute it. Since I am looking at a standard inner product, it is 1 into 1 plus 1 into 2 plus 1 into 1, which is same as 1 plus 2 plus 1, which is 4. Fine. So the angle between these two vectors, cos theta of the angle between them, is nothing but 4 divided by length of u into length of v, which is 4 upon length of u is root 3, and length of this is 1 plus 4 is 5 plus 1 is 6, what it is. So this is equal to 4 upon 3 root 2. Alright. So this implies theta is equal to cos inverse of 4 upon 3 root 2. Fine. So you can compute this yourself. Another example. So I think I had taken matrix A as in R2 as 4 minus 1 minus 1 2. Alright. With this we had that if I define xy as y transpose Ax, then this defines an inner product. We had done that part. Fine. So under this, let us compute the angle between some vectors. So suppose I want to look at the vector 1 1. So I want to look at inner product of 1 1 with 1 2. Suppose I want to look at this inner product, then this is equal to 1 2, because I am looking at y transpose x 1 2, that is 4 minus 1 minus 1 2 1 1, which is same as, fine, 1 2. Now just have to add these two, 1 and 1 means just add these two. 4 minus 1 is 3 and this is 1 here. So this is same as 3 plus 2, which is 5. Is that okay? So this is the dot product between x and y. Now I have to look at x and x to get the length of x and then y for the length of y. So what is 1 1 comma 1 1? This is equal to 1 1 times 4 minus 1 minus 1 2 1 1, which is 1 1 times 3 1. I hope I am doing correctly, because you will find lots and lots of mistake in my calculations. So keep doing the verification. So 3 plus 1 is 4. With 1 2 1 2, if I look at, it will be 1 2 4 minus 1 minus 1 2 1 2, which is same as whatever it is. So let's see. So it is 4 minus, so let me write it because I do lots of mistakes. So 4 minus 1 and multiplied by 2, so minus 2 and 4. So this gives me 2 and 3. So this is 2 3 with 1 2 So it is 2 plus 6, which is 8. Please check, all right, because I must have done a mistake. All right. So just let me look at 4 minus 2 is 2, fine, and minus 2, sorry, minus 1 plus 4 is 3. I hope it is correct, fine. So therefore, in this case, cos theta, cos of theta, which is the angle between 1 1 and 1 2 under this new inner product equals, numerator will come from here 5 divided by a square root of 4 and a square root of 8, which is same as 5 times 2 into 2, that is 4 root 2. Is that okay? And therefore theta is cos inverse of 5 upon 4 root 2. So please check it yourself. I hope I have done correctly. So I would like you to learn them, try to do them. Is that okay? Now let's come to the next idea, what is called projection. Projection of U on V. All right. So I have a inner product, V is an inner product space, and I have got two vectors U and V. I want to look at the projection of U on V. So you have already done this in your school in physics, what is called U cos theta and U sin theta and so on. But let's try to do it with vectors notations here, all right. So this is what I have, fine. So this is my V vector, this is my vector U, and I want to look at projection here. So this is 90 degree with me. So let me write those points here, 0, P, Q, M, all right. So the vector OM is your vector V, OP is your U, those vectors. The number OM is length of V, OP length of, so OP, the length OP is equal to length of U, and so on, all right. If this is the angle between both the vectors theta, then by definition cos theta, so cos theta is equal to, what is cos theta? Base upon hypotenuse. So base is, so base upon hypotenuse. What is base? Base is OQ and the hypotenuse is OP. Fine, this is one. This is also equal to UV divided by length of U into length of V. This is also equal to this. So the idea is to relate these two ideas and get my answers. Fine. Here it is a scalar quantity, here it is a scalar quantity, but I want the projection. So want projections. Projection, what is the projection? Projection is a vector quantity. Vector quantity. Fine. So what exactly we need is, so projection of U on V. This is what it is. Projection of U on V. So what I have to look at? So by definition this will be equal to, projection is nothing but OQ vector. So it is a vector OQ which is same as length of OQ. So this is the length of OQ into the unit vector in the direction of V, all right. So we have to know what is the unit vector in the direction of U. So let's compute that. Unit vector in the direction of, suppose I have got this vector in this. So what is the unit vector in the direction of this? Unit vector means the length of the vector. So unit vector means the length of the vector should be 1, all right. Now under the standard inner product, all right, length of this vector is 1 plus 2 square root, which is the square root of 5. So, if I want a unit vector in this direction, I need to look at 1 upon root 5 into 1 2, fine. Because if I write this vector as v, then length of v square is equal to vv, which will be equal to 1 upon root 5 1 2 comma 1 upon root 5 1 2. This will come out as a scalar quantity, so 1 upon 5, and then it will be inner product of 1 2 with 1 2 will be equal to 1 upon 5 times 1 plus 4, which is 1. All right. So, when I want to look at the unit vector in any direction, I need to look at the vector divided by the length of the vector. So, any unit vector in the direction of v will be equal to v into 1 upon length of v. Is that okay? So, this is what you have to be careful. So, therefore, projection of u on v will be equal to length of OQ into v upon norm of v. Length of OQ in our notation is this, length into v upon norm of v. Is that okay? So, we need to compute this part. So, we need to compute OP is already known to us. What is OP? OP is a scalar quantity, so it is nothing but length of u itself. I want length of OQ. So, let us go back to OQ here, fine. So, from here what I get here is that this implies OQ, which is same as length of the OQ vector, because this is what we had taken. We wrote OP, we did not write OQ, all right. So, since I am writing OP here like this, so OQ here will be length of the vector OQ, fine. So, length of OQ will be equal to OP times this. So, this implies this is equal to OQ is equal to just this OP will get in the numerator, norm of u into uv divided by length of u into length of v. This part and this part cancels out, you get it as uv divided by norm of v. Is that okay? So, this by definition projection is nothing but uv divided by norm of v. This is the projection, the length from here, and then v upon length of v. Is that okay? So, this is same as u comma, again be careful here, you are putting a scalar quantity here. If I am in real number, then this is fine for us. Is that okay? See, if you are in real number, then this number is the length, I can put it inside, this is what I get. Is that okay? So, this is what you have to remember, that the projection is this vector. So, let me write it down for you so that you remember it. So, somewhere, so projection of u on v is, just write u as it is. Since you are talking of projection on v, it is a unit vector in v that I have to look at. So, v upon length of v divided by v upon length of v. Is that okay? So, this is what you have to be careful, you have to understand this part. This is what the projection is, fine. So, again let me look at the diagram that I have. This is my v, this was my u, this was the projection. So, O, P, Q, M, fine. So, I am getting this as the vector which is the projection, fine. Now, what is this vector if I want to find out? This vector is same as this vector, fine. Now, what is this vector? This is minus of this plus this. So, if I want to look at the vector QP, which is the vector orthogonal to OQ or the vector orthogonal to P, orthogonal to V, all right. Then QP by definition is equal to QO plus OP. OP is same as U for me, and this is same as minus of OQ, which is same as U minus u times v divided by length of v into v upon length of v. Is that okay? So therefore, what exactly we have done is, so let's look at this nicely. So I have got the vector u, I am writing u as u minus u comma v upon length of v, v upon length of v, this is one vector, plus just this part u comma v upon length of v, v upon length of v. Is that okay? So I have got two vectors here. What are the two vectors? This is projection on v, this is orthogonal. So what I have done is I have decomposed u into x and y. What do I mean by that? I am writing u as x plus y, where x is orthogonal to v and y is parallel to v. Is that okay? So I have done the decomposition. This is what you have to be careful about. You have to understand what has been our process. So my process has been very simple, that I wanted a projection onto v. I have given a vector u, I have given a vector v, I want the projection of u on v. Fine. Looking at projection on u and v means at this I have to, so from here I am to look at a which is parallel to this like this, and something which is perpendicular to this. So this was your, so this is the vector that is u is, this was the angle theta, you are looking at u cos theta and u sin theta. Fine. So u cos theta is your this part and this is the u sin theta part. So in the language of vectors, I don't talk in terms of there. What we are saying is that I have decomposed u into two things, one which is perpendicular to v and the one which is parallel to v. Is that okay? That is what you have to understand, and idea is very simple. Since you are looking at u with respect to v here, projection, I am stressing it on again and again, it is a very important idea that you have to look at inner product of u with the unit vector v. This is what we have done, u with inner product v here and then multiplied by v. So this gives me the scalar quantity, the length in some sense, and this is the direction of that. So this is the length of the projection. So this part is length of the projection. Why it is the length of the projection? Because this is a unit vector. So when I took the length of the overall, this will give me only one and this will give me the length of the vector OQ. Fine. So I have decomposed u into one orthogonal and the projection. Fine. So let us look at some example to try to understand it. Example. All right. So my question is, determine the foot of the perpendicular from the point Q, which is 1, 2, 3, 4 on the vector one, 1, 0, 0. Suppose I am looking at this. That is my first question. Second is the same thing, but on the plane spanned by the vectors 1, 1, 0, 0, then 1, 0, 1, 0 and 0, 1, 1, 1. So these are the two questions that I would like to answer. All right, and then end this class with some ideas. All right, so let's try that out. So I'm looking at determine the foot of the perpendicular from the point Q, which is this, on the vector this. Fine. So when I'm saying the foot of the perpendicular, again what I'm doing is that I'm looking at the coordinates of the point Q. So sorry, I should have written P here. In my notes it is q, but here I am looking at p here. So this is my vector which is 1 1 0 0. Suppose this is my vector 1 1 0 0 in some plane. This is my vector p which is 1 2 3 4. I have to draw a perpendicular. So this is the point that I am looking at. What is this point? All right. So in our notation this is supposed to be the point q. Fine. So I want to find out this. So what I am supposed to look at? Fine. Just look at the projection. So what is the projection? So projection of projection of 1 2 3 4 on the vector 1 1 0 0. So this by definition is 1 2 3 4. Then I have to look at this vector which is 1 1 0 0 divided by the length of this. Sorry. Alright, so I am not here using the column notation because it will require a lot of space, so I am just writing like this. But at the back of my mind I have everything with respect to column representation. Alright. So this is same as root 2 gets multiplied, it is half 1 1 0 0, and the inner product of these two is nothing but 1 plus 1, 1 into 1 plus 2 into 1 plus 3 into 0 plus 4 into 0, which is same as 2 plus 1 is 3. So 3 upon 2 times 1 1 0 0. Is that okay? So this is the foot of the perpendicular, that's what we are asking for. So I have got this part. Fine. Now I want this on the plane spanned by this. So what do I mean by this on the plane? Fine. So there are two ways of going about it. One way is that, so if I want to look at, so let's try to understand geometrically first. Fine. So if I look at say the point say 1 2 3. So suppose I have the point 1 2 3, then I can write, so 1 2 3 in some sense, if I want to get it in, so projection of, so let me do it for R2 first. All right. So projection of (1 2 3) on the xy plane. All right. If I am looking at the projection of this on the xy plane, we know it is nothing but 1 2 0. Fine. And from where do I get 1 2 0? Yeah, we know this part. How do I get it? So xy plane is generated by the vector 1 0 0 and 0 1 0. Fine. So let us look at the projection of this. So we want to compute projection of 1 2 3 on 1 0 0, and I want to compute projection of 1 2 3 on the 0 1 0, these two. So this by definition is 1 2 3 into 1 0 0. The length of this vector is already 1, nothing to do. So this is same as 1 0 0, you can check here. If I look at this, this is 1 2 3 into 0 1 0. Again the length of this vector is 1, so nothing to do. 0 1 0, which is 1 into 2 times 0 1 0, which is 0 2 0. All right. Fine. So if we look at 1 2 0 is basically sum of this and this. Fine. So this is equal to this and this together. That's all. Fine. 1 0 0 plus 0 2 0. This is one thing. The other way is to think of that you look at, so the other way, will be that from 1 2 3 remove the component in the direction of z axis. Is that okay? So what is the direction component is the direction of z axis? The foot of the perpendicular on z. So what is z axis? Z axis is 0 0 1. So I have to look at projection of 1 2 3 on the vector 0 0 1. So this is nothing but 1 2 3 0 0 1. Again it is a unit vector, so it remains as it is. So it is same as 3 times 0 0 1. So from this 1 2 3, if you look at this, I have to remove. So 1 2 3 minus 3 times 0, 0, 1, which is nothing but 1, 2, 0. All right. So, I have got this 1, 2, 0 once more. Fine. So, there are two ways of doing it. Either I look at the component in each of these directions, or I remove the component which is perpendicular to that. Fine. So, these are two things. Very, very important. I would like you to understand here that these vectors 1, 0, 0, 0, 1, 0 and 0, 0, 1, they are perpendicular vectors. So, these three are mutually orthogonal. So, that is very important that we need to look at mutually orthogonal vector. Fine. So, what I would like you to do is that in the previous example, these three vectors, they are not mutually orthogonal. Fine. You can see that this and this are even not perpendicular because there is one which is common here. Similarly, this and this is not because there is third component common, and here there is second component common. So, we will have to find out something which is orthogonal to all of them. So, if I want to use that idea, so use the previous idea, use the previous idea, need to find mutually orthogonal vectors. All right, and then do the work which was the first part here, that writing it out, or go to something which is perpendicular to it. Fine. So, let us look at this vector. These three vectors are linearly independent. That you can check yourself, there is nothing special, just verify it for yourself that they are linearly independent. Why they are linearly independent? So, be careful. Look at this third component, the fourth component is non-zero here, 0 here, 0 here. So, therefore, this vector is perpendicular to these two. Now, look at this vector, third component, this is 1 here, 0 here. So, therefore, this is independent of this. So, you can check that these are linearly independent vectors, and a plane which contains all of them is this vector x minus y minus z and plus 2w is 0. You can check that. If I put this vector 1, 1, x and y, x is 1, y is 1, z and w are 0. So, this will be 0, 1, 0, 1. So, x is 1, z is 1, the rest are 0, and here it says minus y minus z plus w is 0. So, this is the one that I am looking at. Fine. So, this is the plane which contains all the three. Fine. So, the linear span. So, what I am saying is that look at the linear span of the vectors 1, 1, 0, 0, 1, 0, 1, 0, 0, 1, 1, 1 is nothing but all x, y, z, w belonging to R4 such that x minus y minus z plus 2w is 0. Fine. Normal of this vector. What is the normal vector? Normal vector means the one which is perpendicular to all of them. So, normal vector here is nothing but 1, minus 1, minus 1, 2. Just look at this with the dot product x, y, z, w is this vector. So, this with x, y, z, w is nothing but x minus y minus z plus 2w. All right. Fine. So, this is the normal vector. So, what I can do? I can look at inner product of 1, 2, 3, 4 with this vector that I am looking at 1, minus 1, minus 1, 2 divided by length of this. So, length of this will be 4 plus 5 plus 1, 5, 6, 7, the square root of 7 times this vector again. So, let me use another ink, 1, minus 1, minus 1, 2 divided by root 7. So, this will be 1 upon 7 times this vector which is 1, minus 1, minus 1, 2 into this which is 1, minus 2, minus 3, 4 plus 2 is 8, which is 8 plus 1 is 9 minus 5, 9 minus 5 is 4 upon 7 times 1, minus 1, minus 1, 2. So, therefore, the actual vector that I am going to look at is this vector 1, 2, 3, 4 minus this. So, the answer for the question is 4 upon 7. So, 1, 2, 3, 4 minus 4 upon 7 times 1 minus 1 minus 1 2, which is same as 7, 14, 21, 28 minus 4. So I always do mistakes, so plus 4 plus minus 4, then it is 4 minus 8 divided by 7. So this is equal to 7 minus 4 is 3 upon 7, 3, 14 plus 4 is 18, 21 plus 4 is 25, and 28 minus 8 is 20, this upon 7. So this is the projection that I would like you to try that out. Fine. And this matches with my answer, so my calculations are correct, calculations are correct. So let's finish what I am trying to say. So in place of finding something which is perpendicular to it, I went and found out something which is orthogonal. I could do it because there was only one vector which was perpendicular. Fine. So in the next class what we are going to do is that we are going to find ways and means to understand that given a set of vectors, how do I make them perpendicular? Is that okay? That's our aim in the next class. Thank you.